We are late because of our student who was responsible for today's translation, and I don't see chart yet. Where is chat? Chat. Okay. So today we start next chapter, chapter 5, differentiation. So sections are numerated by lectures, as we agreed before, and today's seems lecture 20, lecture number 20, if I'm not mistaken. So section 20.1, definition and basic definition and basic properties. Of differentiation. Okay, we'll start with definition. So definition. If f g to r is defined on an open set G, i.e. every point of G, every point x in G is contained in G with its neighborhood. So there exists a suitable delta such that the interval x minus delta x plus delta is in G for every point we can find a neighborhood which is in G. Then f is called differentiable at A in G too many ifs in okay, maybe I'll change a little bit English. Let f be defined on an open set, yeah. Then f is called differentiable at a if there exists finite limit x tends to a, f of x minus f of a, x minus a. If f is differentiable, at a, then the limit is called derivative of f at a. So f prime at a equals to limit as x tends to a, f of x minus f of a over x minus a. Okay, in fact, that is very popular question from our examinators to students about definition of derivative. Everybody knows that the limit, the derivative is equal to this limit, and very popular mistake is to say as an answer to a question, give me a definition of derivative. Okay, derivative is such a limit. But there is a very important thing. If the limit exists and is finite, that's important. A little bit later we'll consider also the case of infinite derivatives. It's a little bit different story, but normally for the definition of derivative you should firstly suppose that a finite limit exists, and if it exists it is called a derivative. That's it. Okay, so maybe I'll consider several examples. Okay, example. First, f of x equals to x. F from R to R. Second, f of x equals to x squared. F from R to R. And yeah, a in both cases a is arbitrary. And third, f of x equals to modulo x, f from R to R, but only a equals to 0 is interesting for us in this example. So, first example, we should to check the existence of the limit as x tends to a, f of x minus f of a over x minus a. In our case, that is precisely x minus a over x minus a. and obviously it's the same as 1. Why? Because once again, when we consider the limit, we suppose x is not equals to a, so we can cancel common multiplier in numerator and denominator, which is not 0. And after that, we substitute x equals to a. Okay, and that is precisely f prime at arbitrary point of a by the definition. Next example, we consider the limit f of x minus f of a over x minus a. Here it will be x squared minus a squared over x minus a. Using difference of squares, we can write it down as x plus a over 1 after cancelling common multiplier x minus a. And after that we may substitute x equals to a, so we have 2a, and that is precisely f prime at arbitrary point a. The last example, he will prove that the limit from the definition of derivative doesn't exist. How? Okay, so a is 0, and we'll consider one-sided limits. Limit as x tends to 0 plus f of x minus f of 0 over x minus 0. That is, if x tends to 0 plus, it means x is positive. Hence, modulo x coincides with x. So we may replace by x. F of 0 is always 0. And that is 1. And the limit as x tends to 0 minus of the same difference, of the same expression, sorry, is equal to, here we have modulo x for x negative is minus x. Again, minus 0 over x, and that is x tends to 0 minus 1, minus 1. So those two equalities guarantees that the limit as x tends to 0, f of x minus f of 0 over x minus 0 doesn't exist. Because if we have two one-sided limits and they are different, then the limit doesn't exist. So modulo x is not differentiable at 0. And this last example is a counterexample to show that the condition in Theorem 1 is indeed necessary, only necessary condition. So if f is differentiable, at a, then f is continuous. At a. And proof. So there exists finite limit And if a function has a finite limit, then it is bounded in a punctured neighborhood. So there exists delta greater than 0. There exists a constant m such that for all x in punctured neighborhood, so a minus delta, a plus delta, without a, we have modulo of our function, and our function is that one, is less than m. That is who is it? Sorry, can you delete this guy? Sorry? Ah, okay. You cannot delete.
I can delete the comment, but I cannot delete it.
Oh, really? And I hope he cannot disturb us.
Yes, if there's a right, I will delete
it. Okay. So there was a property that if a function has a limit, then it is bounded in a punctured neighborhood. And we used that property. So, and what it means, let me write it down. Modulo f of x minus f of a less than m times modulo x minus a. Now it is valid, this inequality is valid. Okay, I may write less or equal, and now it is valid in a neighborhood. Why? Because for punctured neighborhood it follows from this inequality, and if x equals to a, then both are zeros, right? Okay, and yeah, in fact now we may conclude continuity of f, since limit as x tends to a f of x equals to f of a, because yeah, you see, if x tends to a by two policeman theorem, let's say, so non-negative, okay, non-negative, and both tends to 0 as x tends to a. So the middle part also tends to 0. So and you see the last example from the first group, modulo x, says that, yeah, you see, modulo x is not differentiable, but obviously it is continuous. So we know if f is differentiable, then f is continuous, but converse assertion is not true, as the example of modulo x shows. Okay, so we can proceed now. Next theorem is about arithmetical properties of continuous functions. So theorem 2 if differentiable at A R, then first assertion, f plus g is differentiable at A, and f plus g prime at A equals to f prime plus g prime. And analogous assertion is valid for the difference, so I'll put here minus, minus, minus. Second, f times g is differentiable at A, and derivative of the product is equal to f prime times g plus f times g prime. Sometimes it is called Leibniz rule, although Leibniz formula is different, usually is different. And if additionally g of A not equals to 0, then f over j is differentiable at A, and derivative of the ratio equals to f prime at A, f prime at A g of A minus f of A g prime of A over g of A squared. These are main rules of differentiation, together with chain rule, which we'll prove later. So, proof. So, since both f and g are differentiable, then f is defined on a set J1, g is defined on a set J2, and there is a neighborhood which belongs to J1 and another maybe neighborhood which belongs to J2, and we can take the intersection and it will belong to the intersection. So all those f plus minus f times g are defined on the intersection. And that intersection is again an open set. For the ratio, we should consider smaller set, but if g of A not equals to 0, then by the properties of the limit, and also we know g of x is continuous at A by theorem 1, if j is differentiable, then g is continuous, right? So from those two properties, it follows g of x not equals to 0 in a neighborhood of A by the properties of the limits. So if the limit is not equals to 0, then the function is separated from 0. So in particular, it is not 0 in a punctured neighborhood, and for continuous function, you may forget about punctured, because at the center it's obviously also is true. So now for the ratio, it is defined from that neighborhood. So this neighborhood, let it be u of A, right? And then this ratio is defined on the intersection of u of A and g1. So in all cases, all those arithmetical operations give us functions which satisfy the first condition for differentiability. Let me recall. So the definition of differentiable function, it starts from the sentence let f be defined on an open set which includes the point where we want to investigate the differentiability. So we checked that condition. Indeed, all those functions are defined on an open set, because the intersection of two open sets is again an open set. It's quite obvious. So, okay. Now we need to check the existence of limits. Which limits? So we start with the first. So now we want to check if such a limit f plus minus g at x minus f plus minus g at a over x minus a exists. Okay, let me transform the numerator just by opening the brackets. So we have f of x minus f of a plus minus g of x minus g of a. Yeah? Minus plus minus, minus plus minus. And that's it. And now we know that those limits exist and are finite. So we can write using the property of the limit of sum or difference is equal to the sum or difference. And lastly, because of definition of derivative, both are equal to the corresponding derivatives, and that is by definition, so this limit exists, hence this is precisely the derivative of sum or difference. Okay, so 1 over g u of a 1 over g, yeah, f over g, yeah, f over g, not 1. So g of a not 0, g is continuous, hence g of x not equals to 0 in a neighborhood. U of a, that is just that neighborhood. It was a property of, firstly, it was a property of limits. So if the limit is not 0, then the function is not 0 in a neighborhood. Moreover, it is separated from, it was a property, so limit x tends to a f of x equals to L, L not equals to 0, then f of x greater than L over 2 in a punctured neighborhood. This was a property for the limits. And for continuous function, we may deduce the same estimate, but now the limit will be f of a. Okay, g of a doesn't matter. So we have g of x, g of a is here, g of a is not 0, right? Hence, this inequality is true. G of x here. This inequality is true for a punctured neighborhood, and obviously it is valid also for the point A. So this is true in a neighborhood, and it means g of x not equals to 0 in a neighborhood. U of a, and now we put here u of a intersected with g1. Why? Because f should be defined as well. Okay? Okay, so now we have proved the first property. The second property. For the product. Here we should consider limit as x. I forget to say that we will continue without break because we lost many time. Too much of time we will have lost. So f of x, okay, I'll write f times g of x minus f times g of a over x minus a. Now let us proceed as follows. So by definition we have f product g of x equals to f of x times g of x. Now I'll add and subtract same expression, let's say f of a g of x, and plus the same expression f of a g of x. So same expression with plus and minus sign, and minus f of a g of a over x minus a. Then I'll proceed as follows. So I'll group two terms in the numerator, and then we separate the ratio into two fractions, and we have then limit as x tends to a. I'll write here f of x minus f of a over x minus a, right, times g of x. And I can write like that. Okay, at the moment this is not a completely correct. I mean, because this will be correct after we'll check that all those limits exist and are finite. After that, everything will be correct. But so here we may put f of a as a common denominator using properties of the limit, put it outside. Now look, so I wrote now an equality which is not correct yet, but look at this. So what we know? This limit exists by the definition because of f is differentiable at a. That limit exists because of theorem 1. G is differentiable, hence G is continuous. And if G is continuous, then the limit exists and equals to the value of G at a. The last limit exists because of definition of differentiability of the function G. So all those limits exist, and then after that, this equality becomes correct. So now this is correct. So, and we can write the values of those limits. We know them. F prime of a, that is g of a, because of continuity, plus f of a times g prime at a. Okay, so second equality is proved. Now let's prove the third, the last. Okay, so we should consider here limit as x tends to a, f over g of x minus f over g at a over x minus a. That is by the definition f of x over g of x minus f of a over g of a over x minus a. Okay, let us transform this expression. We consider the difference by common denominator and then divide one fraction to another, and we obtain then f of x times g of a minus f of a times g of x divided by g of x g of a times x minus a. That is after transformations of that ratio of fraction and a polynomial. So then again we'll add and subtract the same expression. So f of x g of a minus f of a g of a plus f of a g of a minus f of a g of x over g of x g of a times x minus a. Okay, again I'll group the expressions in the numerator in pairs, and now again I'll write an equality which is not correct yet, but later, a little bit later, we'll check it is indeed true. So here I'll put f of x minus f of a outside, then x minus a, and what remains, g of a common multiplier we may cancel with these, g of a is not 0 by the condition, right? So what remains, limit x, okay, I may write like that, divide by the limit x tends to a g of x, using properties of the ratio of limits, plus for the second, analogously, 1 over g of a is a constant, I put it outside, so then here f of a also is a constant outside, and what remains, limit x tends to a g of a minus g of x over x minus a divided by the limit g of x. So what I wrote is not correct yet, but it will be correct. Why? Because now I should check that all limits here exist, and moreover that this limit is not 0. So again we use continuity of g, so limit as x tends to a g of x is equal to g of a, and g of a is not 0, hence this limit is not 0 and exists. And those limits, okay, this limit is precisely the derivative, and the second is equal to minus derivative, because here we change the order. So all limits exist, moreover limits in denominator are not 0, hence we can use properties of the limit, namely we have sum of limits and ratio of limits, also protected by a constant. So we can, the equality is correct now, and we can write the values. So this is f prime at a divided by g of a plus f of a over g of a times minus g prime at a over g of a. Okay, this is a little bit strange writings, but if we divide, we have g squared here in the denominator, and then here we have only one g of a, so we need to multiply to get common denominator, and minus this minus f of a g prime at a. So we have proved. The equality is proved. Okay. Now, yeah. Now, there is a lemma which gives, in fact, in most of textbooks, the assertion of this lemma is precisely definition of differentiability. So, but here, this is just a lemma. Let f be defined in an open set G. Then f is differentiable at A in G if and only if there exists a function u, okay, also from G to R, such that f of x minus f of a equals to f prime, no, sorry, they exist number capital A in R and a function such that A plus u of x times x minus a, and the limit as x tends to a, u of x equals to 0. Proof. So, firstly, let's prove necessary part of that condition. So, if f is differentiable, then f is differentiable. Then there exists limit. The limit x tends to a f of x minus f of a over x minus a exists. Let it be, yeah, that is f prime at a. And let it be a precisely, by definition. Put a, capital A, equals to f prime at a. So, put u of x equals to f of x minus f of a over x minus a when x belongs to G minus the point A itself. And in fact, we can choose arbitrary value of u at the point A. Why? Because, look, for this equality, substitute x equals to a. X minus a is 0. So the right hand side equals to 0, the left hand side equals to 0, and doesn't matter what is the value of u of a. Doesn't matter, absolutely. So the value of u of x at a is not important. For arbitrary choice, the equality is valid. Now, what do we need to check after that? Look, the equality is valid by the definition. We defined a and u of x, and the equality is valid, right? So the only thing we need to check that the limit is 0. Oh, sorry, I forget. Yeah, minus a, of course, minus capital A. Sorry, I forget here. U of x is this difference. So if we substitute, capital A plus u of x is precisely this ratio, so that is by the definition is what we want, right? So what remains is to prove that the limit of u of x is 0, but that is again is true since this limit is a minus a is 0, right? Everything is proved then. Okay, now converse. So sufficiency part. Now we have the equality. So f of x minus f of a equals to a plus u of x times x minus a. So we deduce from here f of x minus f of a over x minus a equals to capital A plus u of x for all x in g minus a. Definitely we should exclude the point a itself, right? Then what we can deduce from this equality? We know the limit of u of x is 0 as x tends to a. So the right hand side has a limit, hence the left hand side has a limit as well. And that is precisely the definition of differentiability. So the function f is differentiable if this limit exists and it is finite. In fact, the limit equals to capital A, so capital A equals to the derivative for sure, right? So if we have this equality with a constant capital A, then this constant is precisely the derivative. The function is differentiable. So the lemma is proved completely. And let me give a remark also. Okay. So remark of this lemma. Remark. We can choose u of z of a equals to 0 in lemma. So it's possible to give an example for the lemma. What means example for the lemma? Every differentiable function is example for the lemma. So first two examples, x and x squares, are examples for that lemma. Okay, so we can choose u of a equals to 0. Once again, u of x was chosen in a way such that the value of at a was considered to be arbitrary. Doesn't matter which value of u at a was chosen, right? And indeed, you see that doesn't matter what is u of x here. But for the future, let us put a restriction. So we'll choose u of a equals to 0 in lemma. It will be important for the next theorem, which is precisely chain rule. So theorem 3, chain rule. If G from G to R is defined on an open set G and differentiable at A in G, G of G is in, let's say, E okay, let it be simple. G of B equals to E. E is open and F is defined on E and differentiable at G of A. Then f of G, composition of functions f and G, is differentiable at A and f of G prime at A equals to f prime at G of A times G prime at A. Proof. So by the lemma, let me write, okay, which letter? Okay, for f I'll use x as it was before. So, but the derivative we want to find at the point G of A for the function f. So I'll write first f prime at g of a times plus u of x, x minus g of a. That is by differentiability of f at the point g of a. That is precisely by lemma, better to say, right? By lemma. And for the function g, we may also write a thing like that. So I'll use another letter t. G of t minus g of a equals to g prime at a plus another function v of t times t minus a. Now look, what we know also, we know that the limit as x tends to g of a, u of x equals to 0, and limit as t tends to a, v of t equals to 0 as well. Now, what we have to do? Okay, roughly speaking, we substitute. So look, here for the equality we can take x arbitrary from the set E, and by our supposition the set E coincides with the image, so every x can be written as x equals to g of t. And if we'll substitute x equals to g of t, then we can proceed as follows. So look now. So it means that f of g of t, so we substitute instead of x g of t, and we can write minus f of g of a equals to f prime at g of a plus u of, instead of x I substitute g of t, brackets are closed, then times, now look, here I have g of t minus g of a, and g of t minus g of a, I substitute the expression from the second equality, so g prime at a plus v of t times t minus a. Okay, let's rewrite what we obtained then. We have f prime at g of a times g prime of a plus u of g of t times g prime at a plus f prime and g of a times v of t, brackets are closed, times t minus a. Denote everything except the product of our derivatives in brackets by W of t. Then we have the desired equality for the composition. So we have f composition G at t minus f composition G at A equals to f prime at G of A times G prime of A plus W of t times t minus A. The question is, so to complete the proof of the theorem, we need to check only that the limit as t tends to a w of t equals to 0. That is the only thing which remains to prove now. So let me write down what we want. Limit as t tends to a w of t equals to, I can write again an equality which is not valid yet, but we'll check its correctness few seconds later. So I'll write limit t tends to a u of g of t times g prime at a plus, okay, I may put constant without limit, of course, limit t tends to a v of t. So this equality will be correct once we'll check that both limits exist. So look, the second limit exists by the condition, by lemma, right? Limit of v of t is 0 as t tends to a. But for the first, it's a little bit more complicated. Why? Because we wrote a theorem about limit of composition. So we may take limits separately in composition if we know that the function d of g of t is not equals to, where we should, not equals to g of a at a neighborhood of a. Definitely we have no information of this kind here. Nobody excludes the case when g of t, for example, is constant. In principle, it's possible. So we cannot refer to the theorem about the limit. But let us look at the function u of g of t. G of t is continuous at a because of differentiability. And u is continuous if we'll use the remark. So if we choose u of now it is not at a, right? U of g of a, right? So if we choose u of g of a equals to 0 according to that remark, right? then the function u becomes continuous as well. So this function is continuous as a composition of two continuous functions. So for continuous functions, no problem with that additional condition for the limit of composition. So u is continuous, g is continuous, hence the composition is continuous, and we may substitute. So we obtain then u of g of a times g prime of a plus f prime g of a times v. Okay, here I have 0, no problem. And now again u of g of a is 0, so we have 0. And it means that the proof is completed, because we have proved, so by lemma it follows that the composition indeed is differentiable, and moreover the derivative is precisely this number which appears in the equality. Okay, theorem is proved. And now, yeah, an example. Example. So h of x equals to 3x power 4 plus x plus 7 power 15. Okay, so I'll start with the proof of, okay, let's start with the proof of this formula. N is natural, right? We'll prove it by induction. By induction. So n equals to 1, we checked. In fact, we checked n equals 2 as well. First two examples were precisely cases n equals to 1 and n equals 2 of that formula at arbitrary point x. Okay, so if we checked that equality for n equals to k, so it means the induction hypothesis is x power k prime equals to k times x to the power k minus 1, then for n equals to k plus 1, we should find the derivative of x to the power k plus 1. So let us write it like that. We have derivative of the product, so that one. By induction hypothesis, we have k times x power k minus 1 times x plus x power k. And both are both powers of x are x to the power k, so we have k plus 1 x power k. That is precisely what we have to prove to complete the proof of that equality by induction, right? Okay, now let us use the chain rule for g of x equals to 3x power 4 plus x plus 7, and f of y, let's say, is y power 15. So h of x is precisely then f of g of x. So by chain rule, we have h prime of x equals to f prime at g of x times g prime of x. Now look, okay, what is f prime? F prime of y, according to the rule, 15 times y to the power 14. And g prime is equal to, if we'll choose also derivative of the sum, and constant can be taken outside of the derivative, 3 times 4x cubed plus 1 plus 0. Derivative of 7 is 0. So we have, if we substitute 15 times, instead of y, I should substitute g of x, 3x power 4 plus x plus 7 power 14 times derivative of g, which is 12x cubed plus 1. And that is the answer. Okay, that's all for today. Thanks for your attention.